we are looking at MEMO, Memory as a Model by Ryan Wei Hengquick, Sengyak Lee, and their collaborators at NUS, MIT, and others.
Yeah, and if you are building AI systems right now, you know the absolute headache of getting a frontier model to learn new facts.
Right, without completely breaking its brain or, bankrupting your compute budget in the process.
Exactly. And this paper introduces a framework that just completely sidesteps those issues.
It's super interesting. Basically, it splits a large language model into two distinct parts.
Right, so you have a frozen executive reasoning model.
So think like Qwen 2.532B or Gemini 3 Flash.
Yeah, and then a dedicated, much smaller memory model. So instead of retrieving raw text chunks like you do with RAG.
Or fine-tuning the massive model, which we know causes issues.
Right, you train the tiny memory model exclusively on a synthesized reflection QA data set that represents your new corpus.
And then in inference time, that frozen executive model uses a structured multi-turn protocol to basically interrogate the memory model for facts.
Yeah, and the result, it just crushes state-of-the-art graph RAG on cross-document reasoning.
Oh, completely. It's immune to retrieval noise, and it lets you do continual updates via model merging without even touching the big LLM.
It's massive.
So yeah, welcome to AI Paperslop. Let's get right into it.
It really is a radical shift in how we handle knowledge architecture.
Yeah, and to really appreciate why isolating memory like this is such a big deal, we have to look at the three paradigms we've been relying on.
And why they all fail, frankly.
Right. So if you're an ML engineer, you've definitely fought with these. The first paradigm is non-parametric, so mostly Retrieval-Augmented Generation, or RAG.
Yeah, RAG, where you just leave the weights alone, chunk your documents into a vector database, and shove whatever looks relevant into the context window.
But RAG has a really fatal flaw with deep synthesis, right?
It really does, especially across long context. Because if you ask a complex question that requires connecting a clue in, say, document A with something in document Z,
it just fails.
Right, the retriever works on semantic similarity, so it grabs document A, but it totally misses Z. The reasoning model is just left blind.
And if you just feed more documents into the context window, the model's attention gets completely diluted.
Yeah, the paper actually shows that if you introduce distractor documents, the performance of even advanced RG systems just drops off a cliff.
I always think of RG like taking an open book test. You have the textbook, but you are physically incapable of synthesizing Chapter 1 with Chapter 10.
That's a great way to put it. You're just frantically flipping pages.
Yeah, scanning for keywords, but totally missing the plot.
So to fix that, people turn to the second paradigm, which is parametric. Supervised fine-tuning or continual pre-training.
Right, which solves the synthesis problem because you're baking the knowledge right into the neural weights.
But then you hit catastrophic forgetting.
Exactly.
Yeah.
You update the weights of a massive model to learn, legal or medical data, and you overwrite the very weights that hold its basic reasoning.
It degrades the safety alignments too, right? Oh, totally. Plus, the scale is just prohibitive. You simply can't afford to run full fine-tuning on a 70 billion or 400 billion parameter model every single time your company gets new PDFs.
Yeah, fine-tuning is like studying so intensely for a biology exam that you literally forget your own name.
Exactly. The structure is damaged.
Which brings us to the third attempt, latent memory. So things like auto-compressor or gist tokens. What's the bottleneck there?
Well, latent memory tries to mathematically compress the context into these soft tokens. So you pre-compute a dense vector of the documents.
Which is great for the context window.
Highly efficient, yeah. But it suffers from representation coupling.
Meaning it's tied to one specific model.
Right, because those tokens are generated by the exact attention heads of one specific architecture. You can't take a gist token from a Llama 3 model and use it in a Qwen model.
So it's like writing your study notes in a proprietary cipher.
Yeah, totally useless if you want to hand them to a smarter reasoning model.
So, okay, RAG is too fragmented. Fine-tuning destroys the brain, and latent memory is locked in a cipher. How does MEMO actually fix this? Because, aren't we just training a smaller model? Isn't that just fine-tuning again?
The secret isn't just the model size, it's what you feed into it. They completely decouple the raw text from the training process.
Oh, interesting.
Yeah, instead of fine-tuning the memory model on raw paragraphs, they use a highly capable generator model like Qwen 2.532B to distill the whole corpus into a reflections dataset.
Right. It's a QA dataset built through a very specific pipeline.
Exactly, before the memory model ever sees it.
So let's break down that pipeline, because going from raw PDFs to a pristine dataset seems to be where the magic is.
Yeah, the generator model basically makes multiple passes over the text. First, it extracts facts.
Direct facts and indirect facts.
Right. Direct things stated plainly and indirect ones that require a little inference. But if you have, say, thousands of financial reports, you'll extract the same entities over and over.
Right, so how does it not just choke on all those duplicates? Does the memory model just learn the same fact 500 times?
No, and that's where the consolidation phase comes in. The pipeline actively looks at all the extracted facts and merges overlapping info.
Oh, I see.
Yeah, if 50 extractions mention the same corporate merger, it consolidates them into comprehensive multi-fact QA pairs. And then it does strict verification.
So checking if the questions make sense in a vacuum.
Exactly. Like if a raw question asks, what did they propose in the meeting? The pipeline rewrites it to specify who they are.
And which meeting it is.
Right. If it's ambiguous without the source document, it gets rewritten or just discarded.
That makes sense. And there's another really cool step here about the reversal curse.
Oh, yeah.
Because, large language models really struggle to work backwards. If you train it that Tom Cruise starred in Top Gun and then ask who starred in Top Gun, it stumbles. The mapping is directional.
Yeah, the associative mapping only goes one way.
So how does the reflections pipeline fix that?
It actively attacks it through entity surfacing. The generator purposefully creates questions that force the model to identify an entity based purely on its traits or actions.
So building bidirectional pathways.
Exactly. So the memory model has a robust map of the facts, not just surface-level memorization.
But wait, the real hurdle with ARG was connecting disparate clues across different documents.
Right. Cross-document synthesis.
Yeah, how does this pipeline teach a tiny model to do that?
This is the breakthrough. The pipeline hunts for converging clues across totally different chunks of text. So imagine document A says a specific titanium alloy degrades at 400 degrees.
Okay.
And document Z is an incident report where an engine hit 420 degrees right before a failure, but it doesn't name the alloy.
Ah, so ARG would miss that.
Completely. But the synthesis pipeline connects those properties and generates a training question like, which alloy likely contributed to the failure based on its temperature limits?
That is brilliant. It builds the logical bridges beforehand.
Yeah, and crucially, they strip out all document identifiers.
So no shortcuts.
Right, the memory model can't just memorize that the answer is in document ID 405. It has to actually learn the relationship between the alloy and the temperature.
Looking at the ablation studies, what happens if you skip that cross-document synthesis step to save time?
The accuracy just collapses. On the narrative QA benchmark, which is incredibly dense, removing that step dropped performance from 24% down to just 6.37%.
Wow. Wait, really 6%?
Yeah, 6.37. It is the single most critical mechanism in the pipeline. But there is a brutal trade-off. That synthesis step scales quadratically in compute cost.
Because of the combinatorial explosion, right? If you double your
Yeah.
chunks, the compute explodes because it has to search every possible pair of facts.
Precisely. It's big O of K times C squared times Q squared. It is heavy upfront.
But the performance collapse proves you have to do it.
You pay the compute tax once during generation, so your inference is flawless.
Okay, so we've run this heavy pipeline. We trained our tiny, let's say, 1 billion parameter memory model. The knowledge is baked into the weights. But here's the mechanical question. At inference time, how does the frozen executive model get that info out? There's no vector database. How does it know where to begin?
It uses a highly structured, multi-turn protocol. It's not just a single prompt. It acts way more like an agentic loop.
Okay, walk me through that. User submits a query, then what?
The executive model gets a strict three-stage process. First is grounding. It looks at the complex query and decomposes it into simple sub-questions, like a detective.
Right.
And it fires these at the memory model. Now, during this phase, the memory model's temperature's dialed way down to 0.1.
So very deterministic.
Exactly. No hallucinations, just facts. But the executive sits at 0.4, so it has enough creativity to formulate the probes.
So fires probes, gets facts back, but what if it gets a dozen candidates that match?
That triggers stage 2, entity identification. The executive uses the initial facts to narrow down the candidate, and if it hits a dead end, like the memory model fails to corroborate something, the executive tracks these uncertain answer streaks.
Oh, so it keeps a running tally in its context window.
Yeah, and uses that tally to actively prune the search tree.
It's essentially deductive reasoning.
Exactly. And once it isolated the entity, it enters the final stage, answer seeking and synthesis.
Does the temperature change there?
Yeah, the executive model's temperature gets cranked up to 1.0, maximum creative freedom to synthesize the final answer for the user.
What's so wild about this is that it's just passing text back and forth.
Right, completely model agnostic.
Yeah, you can use a closed source API like Gemini 3 Flash as the executive. You don't need its weights, you just let it talk to your local memory model.
It's pure plug-and-play modularity. You decouple storage from cognitive reasoning.
Okay, but does this complex interrogation loop actually beat standard graph R in the benchmarks?
Oh, absolutely. They tested it on BrowseCon Plus, Music, and Narrative QA.
And narrative QA is the hardest one, right? Median document lengths of like 66,000 tokens.
Yeah, you're asking it to follow threads through entire books. Standard R grounds that because the context window just fills with noise.
Right.
But MEMO, using Gemini 3 Flash as the executive, MEMO hit 53.58% accuracy.
Wow.
Compare that to HipperRAG 2, the state-of-the-art graph RAG, which only got 23.21%.
It more than doubled the performance.
Exactly.
Okay, but let me play devil's advocate. Looking at the data for BrowseCon Plus, when they used the open source Qwen model as the executive, HipperRAG 2 actually beat MEMO slightly.
Yeah, 56.Leon to 54.22.
Right, so why did MEMO lose there?
It's a great catch, and it's a very specific edge case. BrowseCon Plus tests multi-hop reasoning on facts completely absent from the executive's pre-trained memory.
Okay.
So with a slightly weaker reasoning model like Qwen, actually seeing the raw retrieved documents, which RAG literally pastes into the prompt, gives it a slight edge.
Because RAG hands it the raw source material to read, but MEMO needs the executive to be smart enough to ask the right questions.
Exactly. The oracle is only as good as the detective. If the detective has bad questions, the memory stays locked. But when they swapped Qwen for Gemini 3 Flash, MEMO shot right back up to lead with 66.67%.
That makes total sense. And we have to talk about the noise problem. In an enterprise database, you have so much garbage data. Outdated memos, irrelevant stuff.
And standard retrieval collapses there. The researchers scaled the noise from 0n to 1n and then 2n, basically flooding the corpus with distractors.
And what happened?
RGAG methods like embed v2 and HipperRAG 2 degraded sharply. As soon as you add distractors, they drop by 5 to 11 percentage points.
Because irrelevant documents get retrieved by mistake.
Right, and it dilutes the LLM's attention. But MEMO remained completely stable. The accuracy did not budge.
Because the executive never sees the noisy documents, it only sees the synthesized answers from the memory model.
It's an impenetrable firewall against data noise.
That is huge for production. But okay, thinking about continuous integration, if a new batch of PDFs drops tomorrow, do I have to run that massively expensive quadratic pipeline over my entire historical data set again?
No, you don't.
Oh, thank God, because that would be a deal breaker.
It's probably the most critical engineering contribution here. They solve it through model merging. You only run the synthesis pipeline on the new data. You train a brand new memory model on just those new reflections.
You create a task vector.
Right, a mathematical representation of the weight shifts needed for just the new corpus.
And then you just merge the weights.
Yeah. They tested 14 different configurations and found that ties merging worked best, specifically with a sparsity factor of 0.3.
For people who haven't used ties, how does it combine the vectors?
It aggressively sparsifies updates and resolves sign conflicts.
Right.
So training creates millions of tiny weight shifts that are just noise.
Right.
Ties throws away the smallest changes, that's the sparsity factor, and keeps the strong signals.
And the sign conflicts.
If the base model says a way should go positive, but the new task vector says negative, they'd normally cancel out and destroy the capability.
Yeah.
Ties forces a consensus on direction before merging.
It's like combining skill trees in an RPG. You just snap on a new skill module without re-leveling from level 1.
Exactly.
What are the compute savings?
Massive. For 2 datasets, merging saves 33% of the compute, drops training from 72 GPU hours to 48 on an 8x100 setup. And if you merge 10 datasets, it's a 5.5x compute saving.
But wait, throwing away subtle shifts and forcing consensus? There has to be an accuracy tax.
There is. On narrative QA, with the Qwen executive, accuracy drops from 26.85% with full retraining down to 15.81% with the merge model.
Ouch. A 10-point penalty.
It's steep. But the critical thing is that even with the penalty, the continually updated memory model still outperforms all standard retrieval baselines.
So you sacrifice some precision, but you keep the deep reasoning and save your compute budget.
It's a very pragmatic trade-off.
Speaking of pragmatic, we need to warn people about the implementation catch here, the LoRA versus full SFT issue.
Oh, this is a classic architectural trap.
Because to save memory, they tested training with parameter-efficient fine-tuning, specifically LoRA, right?
Yeah, and for the LFM 2.5 1.2b instruct model, full SFT hit 37.2% 0.33% on BrowseCon Plus. But with LoRA, it literally collapsed to 0.78%.
Less than 1%. How does an industry standard like LoRA fail that hard?
It's a mismatch with the architecture. Standard LoRa targets traditional Llama-style projection layers, like QProj and vPride.
Okay.
But the LFM 2.5 model has a hybrid architecture. It heavily uses state space convolution blocks, called short-con.
And the LoRA script just sails right past them.
Completely ignores them. The short-con blocks handle the local token mixing, and because their names aren't in the LoRa default targets, they stay completely frozen.
So the model is trying to learn facts, but its core feature extraction is locked.
Exactly. So if you're building MEMO on hybrid architectures, you have to custom tailor your LoRa targets to hit those active convolution layers.
That is such a crucial warning. But stepping back, what about capacity limits? If we keep merging and fine-tuning, won't a 1.5 billion parameter model eventually just fill up?
Yes, that is the ultimate ceiling. In these experiments, they didn't hit it. But mathematically, a fixed-size neural network can only compress so much before it starts hallucinating or overwriting.
So scaling the memory model dynamically is the next big research area.
Exactly.
To wrap this all up, MEMO gives us a universal plug-and-play memory module. You endure the compute pain once to build it, and then you just plug it into any frontier LLM without touching the reasoning weights.
It perfectly isolates knowledge from reasoning, sidestepping arg noise and fine-tuning destruction.
Which leaves us with a really provocative final thought. If we can isolate memory like this, what does it mean for the future of proprietary tech?
It changes everything.
Right. Imagine a near future where domain experts like law firms or medical boards don't sell you an API key for a massive model. What if they just sell you a memory task vector?
It's just a downloadable weight diff.
Yeah, a 50 megabyte file of pure distilled knowledge. You buy it, download it, and snap it into your own local reasoning agent. We could be looking at the total commoditization of domain expertise in AI.
You're just hot-swapping the brain's hard drive whenever you need a new skill. It completely inverts AI economics and privacy.
Exactly. The whole landscape shifts. So keep that in mind next time your standard R8 pipeline drops context. We'll catch you on the next deep dive into the slop.